Look at this beautiful picture of the Mona Lisa. It looks so straight up beautiful on a portrait mode, and everything is aligned, everything is perfect. The sizes of the tree is bigger than my screen sometimes. So what if I want to shrink this image? What if I want to, let's say, rotate this image? What if I want to expand this image, skew this image? Here where eigenvectors come in place. So look, this image, after it was 90 degrees to the vertical, now it became skewed like that. And here we would learn today the eigenvectors. And yeah, read it again with a better font. In linear algebra, we spend a lot of time crunching matrices. We multiply rows by columns until our heads cramp, but we often miss a story. A matrix is just not a box of numbers. It's not just these numbers you see by 1, 2, 3. It's not a telephone sign of the hash. It's something even greater. It's the image itself. It is the transformation of space. So that's how the machines understand the multiple cells next to each other, like the nodes within our face, the eyes, the mouth, the nose, and all of these. So most of vectors, like the first on this first arrow here, this one, most of these are get knocked off of their path when they transform, when the transformation hits them. They change direction, but they are special ones. So when we want to transform this image to expand it, we can transform it to become on that form like that. So we want to expand this image as we have expanded or distorted at some point this image here. So there's a few chosen vectors that refuse to be knocked off. Of course, they might get longer, they might get shorter, and they might flip 180 degrees. Yeah, they stay on, but anyways, on their original span. So these are eigenvectors. These are the eigenvectors. Okay, so and the amount they stretch or shrink is the eigenvalue. So these movements are eigenvectors, but the amount or the value they shrink with is the value itself, obviously. Okay, so today we're just not just calculating them. We are going to see how they actually what they actually are and why they are one of the important things to understand in a matrix. So let's banish the algebra for a second, and we want you to imagine as a spinning globe. So let's say this is the Earth, and here is the axis. Yeah, here's the axis of the Earth. It's not, the axis is not perpendicular. Yeah, it's with an inclination here. Yeah, there's an inclination between the elevation angle, as they call it. Yeah, so every single point on the surface of this Earth is moving. Yeah, correct. If you draw a vector from the center of the Earth to a city equator, let's say America is here, for instance, and you draw an arrow to the center of this equator, or on the equator, yeah, the city, after a few seconds later, the vector is pointing somewhere else. So America is gonna be, for instance, here now, and it's gonna be pointing on another way. Yeah. So, but is it like that? Any vector is changing its direction? So yeah, this is the axis rotation. A vector pointing straight through the North Pole stays pointing always upwards, straight up, no matter how fast the Earth spins in transformation or rotation. The axis is the eigenvector. Yeah, so the axis here is the eigenvector. It's always gonna be pointed upon. Yeah, so this is the secret. Like eigenvectors are invariant axes of the transformation. They feel the origin of the matrix. So if you push a bridge, how does it naturally want to bend? Is the eigenvectors. If you push a bridge, the bridge usually wants to bend by the weights upon of it. This weight, or this vector pointing downwards, is the eigenvector. But let's say let a quantum system evolve, if this system is stable or not, this is the something called eigenstate. Yeah, and if you search Google, which website are the hubs of the internet, for instance, eigenvectors of the web graph. We don't want to go. We don't want to make it that complicated, so we will go on with the mathematics itself. So okay, let's translate the intuition to a famous equation we usually know. Let's say we see this graph here, and this graph here gets an arrow of x. If I want to make this arrow become an eigenvector, I want to expand this arrow, then I would require the eigenvectors to become an AV, where AV is equal to lambda v. This is v, okay? This x is v. So this is our transformation of the matrix. It acts on a vector v, and usually a times v times given totally the new vector, yeah. But our special eigenvectors, the result is simply lambda, as lambda is a scaling factor. Yeah, the scaling factor is called lambda. It is nothing but a number, and v is the origin vector. Yeah, so we have all what we have done is we have took our original vector here, this one, and multiplied it by a scaling factor lambda. Yeah, so the equation literally says matrix A is acting on vector v on the same, just scaling vector v by a number lambda. Okay, so how do we calculate it now? To find this magical vector and numbers, there is a 3-step process usually we do. Let's do a 2x2 example to make it a little bit simpler. So let's say we have a vector of a. Okay, a is equal to 4, 1, 2, 3. Okay, then the characteristic equation is the first thing we want to find. Is something called the characteristic equation. So characteristic equation is what we need to find to find the lambda itself. We want to now find the lambda, so such that AV minus lambda v is equal to 0. That comes from this equation. If we got the lambda on the other side here, it will become AV minus lambda v is becoming to 0. Then, so as we want to find that, we don't want to get we want to get a non-zero solution, yeah, to subtract from the lambda value. So we set this as a determinant to 0. So determinant to 0. It's like the result of it, but we don't want to get it to 0. So it's lambda times I. I is the it's a vector of ones. Okay, so it's as if we have done nothing. It's like we have multiplied something by 1, as if we have multiplied it by 1. So now we're gonna do the determinant now for a minus lambda I. So now the determinant becomes 4 minus lambda times 1, lambda, 4 minus lambda 1, 2, 3 minus lambda equals to 0. So this is our new determinant. So now we want to find the eigenvector. The eigenvalues is now 4 minus lambda times 3 minus lambda minus 1 times 2. What we did here is that we have multiplied this by this, then we have subtracted this from the multiplication of this by this. Yeah, so now it's 4 minus lambda times 3 minus lambda minus 2 times 1. Yeah, so that was the next step. So by that we can find the lambda as polynomial equation, lambda square minus 7 lambda plus 12 minus 2 equals 0. So now the lambda is equaling to lambda is equal to 5 and lambda is equaling also to 2. So what does two values mean? It means that one direction that stretches by 5x and another that stretches by 2x or 2v. Yeah, so now after we have found the eigenvalues themselves we want to find the eigenvectors. So we will plug these values now to our original equation. So subtracting this by 2 from the diagonal of our matrix, so it's going to become 2 1 2 1 x y equal to 0. Okay, yeah, after we have used our lambdas here. Yeah, so now our eigenvectors or eigenvalues are now, let's multiply this, so it's gonna become 2x plus y is equal to 0. Then that means that y is equal to negative 2x. Okay, that means that y is 2 times negative 2 times smaller of x, which means that v is here 1 and negative 2. Yeah, okay, so now it's v is equal to 1 and negative 2. So the vector now is 1 and negative 2 on a grid. Yeah, why do we even care for what we have just talked even about? That's the important part. So for an engineer or a data scientist, we are obsessed over this. Every physicist or physical object on a bridge, a building or a molecule has a natural mode of vibration. These modes are eigenvectors of the system's stiffness matrix. So frequencies usually vibrate but at a certain vibration or a certain frequency. So at that certain frequency, this frequency becomes our eigenvector. Yeah, so it becomes our eigenvalue, this certain frequency. Yeah, and this system stiffness matrix is the eigenvector. So if the wind hits the bridge at an eigenvalue frequency, that means it's a disaster. Yeah, if this disaster comes in, it means that it hit on this frequency. We don't want it to hit on that frequency. This is the eigenvalue here in engineering or in civil engineering. But what if it was for software engineering, for instance? So let's say a Google page rank, the algorithm that Google has built treats the entire internet as a massive matrix. This entire internet is nothing but a great matrix of data. Okay, so what is the importance of this? So the importance of these websites is essentially an entry to the dominant eigenvector of the matrix. How important this website is. So this eigenvector of the matrix is the thing that is determining how important this website is, and it connects the other websites with eigenvalues. Yeah, so eigenvalues is not an abstract algebra variables. They are principal axes of the universe. So these principal axes of the universe, they tell us where the action is in a system, where the stability lies, how things naturally do move. Or next time you see a matrix, don't just see a grid of numbers. Look at the arrows that stay true. Yeah, so I would like to say that this is all for today, but like for now, yeah, we can say that the moves itself or the steps for itself for solving any eigenvectors or eigenvalue is doing the determinant of A minus lambda of I equals to 0, then finding the roots. This is first thing, then roots, then after the roots we find the null space. Null space, we mean by that we find each eigenvector itself, yeah, this the equation by x and y, and we did up there, yeah, the by I here, I for I a minus vi x equals 0, yeah, and we do, and the last thing we do normalize, which is something optional sometimes in many applications like quantum mechanics, and sometimes in PCA. We usually scale the vector to have a length of 1, yeah. So yeah, so thanks for watching, and if you want us to apply the principles of component analysis, like which I mean by PCA here, principal component analysis problem, let me know in the comments, and I hope you tell me if there's something I can improve. And thank you for watching, and I hope you have a nice day. Thank you.